Hello everyone, my name is Sahar Mazloom from George Mason University, and I'm going to share the results of our work on secure power computation on national scale volumes of data. Every day we generate huge amounts of data which are mostly sensitive, such as medical or financial records. Service providers look at our data and clear to run some machine learning algorithms in order to provide some services for us, such as movie recommendations or targeted advertising. But at the same time, they put our data at the risk of data breach. One of the promising solutions to protect our data that has been around since World War II is using cryptography. But how can we still use and compute on our data while it is encrypted? Secure multiparty computation is a branch of cryptography with the goal of creating methods for parties to jointly compute a function over their inputs while keeping those inputs private. That function F can be a machine learning algorithm that parties are interested to run on their encrypted data. Matrix factorization is a nice example of a machine learning algorithm that has been extensively used by major companies and content providers as a building block for the recommendation system. In matrix factorization, the goal is to factorize the matrix of ratings as the product of two lower dimensional matrices of users and items. And the model is trained by using the gradient descent method, which is a popular optimization algorithm and being used in many machine learning computations, such as support vector machines, deep learning, and many others. In gradient descent computation, the model parameters will be updated iteratively until a local minima is reached. For instance, in a movie recommendation system, imagine a rating matrix consists of rating values given by users to different movies. In order to decompose the matrix R into matrices U and V, we should minimize the objective function by computing and updating gradient values of users and movies in each iteration. We looked into machine learning community to understand how these ML algorithms can be trained faster. And we learned that graph power computation frameworks, such as MapReduce or PowerGraph, can help us. The idea is cute and simple. If we can model our problem as a graph, then we can solve that problem by applying the following simple operations on our graph. In the frameworks, the data is assumed to reside in a graph structure, and the result of computation is reached through an iterative process. It's called gas model operation, which stands for gather, apply, and scatter. At first, the data is gathered from all edges to their neighboring nodes. Then, in apply phase, the computation is applied on the data at each node. That computation could be computing gradient descent values. And finally, the processed data is scattered back to the neighboring edges. And then the next iteration starts. There is a work done by Naik et al. That proposed a secure version of this graph power computation framework called Graphicsy. Assume all the data in the graph is already encrypted. So in order to preserve the privacy of data, they only need to hide node degree and edge structure of the graph. In order to do that, they added an extra operation to the framework and call it oblivious sort, which is a secure sorting algorithm. It costs n log s squared n computations, which is fairly expensive if n is large. Applying their framework to compute matrix factorization on a matrix of size 1 million ratings with 6,000 users and 4,000 movies takes almost 13 hours. So the primary question we asked in our previous work was, can we make secret computation algorithms faster if instead of having full security, we allow something small to be learned by the attackers and then prove that what is learned is differentially private? We were the first to explore the idea of relaxing the security notion in secure computation by allowing some leakage in the form of access pattern that preserve differential privacy. Since we assume the data is encrypted, to hide the node degree, we only need to create some dummy edges and then just shuffle them to the real ones to hide the graph edge structure. The number of dummy edges is determined by differential privacy parameters epsilon and delta. And our secure shuffling operation takes only n log n computations which cost a log factor less than oblivious sort. Using this new operation, we designed our own secure graph file computation framework and called it obligraph. The scenario is that, imagine users submit their signature data to two untrusted non-colluding computation servers. Let's say one could belong to Amazon, the other could belong to Google. Obligraph consists of secure version of shuffle, gather, apply, and scatter operations, can reduce the time of computing matrix factorization on the same input size from 13 hours to 2 hours. Note that both of these frameworks that we talked about are only secure against honest but curious adversaries. Now in this work, we ask this question again: can we do better? Can we improve the performance further? Several results in secure computation have recently minimized the communication cost by restricting the number of computing servers to 3 or 4 servers, assuming security with honest majority. And when representing the computation as an arithmetic circuit over a ring, as we do here, the cheapest of these results, by Gordon et al., requires sending only 1-point ring elements per party per circuit gate. So by leveraging the results of low communication MPC and the security relaxation from our previous work that allows the computation servers to learn some differential privacy leakage about inputs, we were able to construct an MPC protocol that can improve the same computation of matrix factorization even further to less than 25 seconds. This protocol also can perform at larger scale data. For example, we can compute matrix factorization on matrices with size 20 million records in less than 6 minutes, or even compute histogram or counting problem on 300 million users, like what they can compute in census data gathering, in almost 4 minutes. To achieve these results, inspired by Gordon et al. And using 4 computation servers instead of 2, we could design a linear oblivious shuffle instead of a quasi-linear one. Also, we replaced the Boolean circuit with a fixed point arithmetic circuit to compute, for example, gradient descent values easier. In addition, we made our scheme secure against one active adversary as compared to the previous schemes that could only support semi-honest adversaries. However, merging these constructions wasn't like plug and play, and it had its own challenges. For example, to preserve the privacy of users' data, the party that was responsible to access data shouldn't learn the shuffling pattern. So to solve that issue, we partitioned these tasks between 2 groups of parties. The first group is doing the shuffling, while the other group is accessing the data. And I'll show it to you in the next few slides. Another challenge was protecting the scheme against an active adversary. And for that, we had to be able to detect the malicious behavior by verifying the results of each operation at each step. So imagine we have 4 parties, Alice and Bob, Charlotte and David, and every operation done by one group is being verified by the other group to detect cheating behavior. So for example, when Alice and Bob perform an oblivious shuffle, Charlotte and David will verify the correctness of that operation. And the same verification happens for gather and scatter. The apply is different. The apply phase, which is computing the main functionality, should be handled by all 4 parties. And then they all help to verify its result by using a cross-check validation step. Our new design framework has reduced the cost of oblivious shuffle operation by 230 times and obliv apply by 830 times as compared to the previous scheme obliv graph. And finally, one of the other interesting challenges we faced was doing arithmetic operations on fixed point numbers. Doing addition on fixed point numbers is easy. Our challenge was when we wanted to do multiplications on decimal numbers, which requires truncation. And let's see how truncation became a challenge for us. During the apply phase in our scheme, each group computes on their masked data locally, and then do a cross-check validation to compare the results to make sure nobody acted maliciously during computation. If the results don't match, they abort. But since in our computation, we are dealing with decimal numbers to compute gradient descent values, for example, in some occasions, the computation may result in different truncated values. and the cross-check validation will fail and parties consequently will abort, but not because of malicious behavior, only because of mathematical errors. We found a way to handle the truncation error securely without any additional overhead, and we discussed the details of that in the paper. We implemented our framework and ran it on different input sizes for histogram and matrix factorization problems. The differential privacy parameters are set to epsilon 0.3 and delta to be 2 to the negative 40. To recap on the results, our framework can securely compute histograms over 300 million users in about 4 minutes and compute sparse matrix factorization on 20 million records in less than 6 minutes. And here is a comparison of its running time with the previous solutions. To conclude, the goal of this work was to show how we can learn on larger scale data with security and privacy. We designed a privacy-preserving machine learning framework that was secure against one malicious adversary, and we used differential privacy to improve the efficiency of our framework. Thank you very much for your attention, and I'm happy to take your questions.